Hello elements, welcome to podcast for review on Unit B. Unit B has chapters 5 through 7 and 22-23. So 5 to 7, so Unit B is mostly about thermochem without the delta G or delta S, which we deal with in second semester. And chapter 6, which is about Bohr's model and spectrum and nature of those, and then chapter 7, which is periodic properties. Okay, so let's start with Unit B's review. And again, for detailed review, please look at the PowerPoints. What I'm trying to do here is bring the main concepts together for Unit B in form of a concept map, so you can see how different concepts fit together and what are the important things in each concept. I do want to tell you or remind you that this is not a comprehensive review, but rather just a quick glimpse of everything you've done in Unit B. Alright, so let's get started here. In Unit B, at the heart of Unit B, we talked about atomic structure. So in Unit A, most of the discussion was about matter and structure of atom. Now Unit B goes a little bit more in depth. Okay, if there is atom and all the matter is made up of atom, what is the structure of this atom? And what does it look like? So I'm going to start with just a brief historical perspective of atomic structure. So there are maybe early theories is what I'll call them for structure of atom, and these early theories involve Rutherford, Dalton, Millikan's oil drop experiment, right? Bohr's model of atom. All of these are early theories, and you should have a good idea of what each talked about. The main idea behind Dalton's atomic theory was that atoms are like marbles, small indivisible particles. Atoms of one element all look alike, and atoms of different elements are different from each other. Rutherford was the first one to give you a model, nuclear model, and he said in the center of the nucleus is a very heavy and small positively charged nucleus, and most of the space in the atom is empty. And he said if the atom is the size of a football field, then the nucleus is the size of a grape. Robert Millikan actually calculated the charge to mass ratio of an electron, and Bohr's model was planetary model of atom, where he said that in the center within the nucleus protons and neutrons are present, and around the nucleus the electrons go around in specific energy levels, which he called as orbits. And the energy of an electron within the energy level is the same unless the electron absorbs energy to jump to a higher energy level or releases energy to jump to a lower energy level. So remember, Bohr's model was very successful because it could explain atomic spectrum of hydrogen. Now, just talking about atomic spectrum, first let's clarify what this is. Atomic spectrum can be of two types, emission or absorption. And both of these together make up a discrete or line spectrum. And then there is another type of spectrum which is called continuous spectrum. Continuous spectrum has all the wavelengths in it, like the solar radiation. But line spectrum has only certain wavelengths in it. When you see the lines as the emitted light, we call it emission spectrum. When you see the lines as the absorbed light, we call it absorption spectrum. So emission spectrum, you'll see dark background and some bright lines interspersed. And absorption spectrum will be bright with some dark bands where the wavelengths have been absorbed from. Absorption and emission spectrum. So Bohr studied hydrogen's emission spectrum. and he could actually explain and theoretically calculate and show the energy of transition of the electron in hydrogen. And that was a very well accepted model, except it had a big problem. It could explain the emission spectrum of hydrogen but not of multi-electron atoms. And Bohr's model calculated the energy of electron in any orbital, E, energy of electron in an orbital, as negative 2.178 value of delta H, Rydberg's constant, negative 18. N squared, right? Let me just minimize this for a second. And let me populate this. And let's go back for a second to PowerPoint of Chapter 6, which is about Bohr's model. I just wanted to clarify that it's negative RH over N squared, right? So this is the Rydberg's constants value. And I did want to clarify this one as well. Negative RH 1 over NF squared minus 1 over NI squared. Okay, let's get back to our presentation. Alright, so this formula is negative RH over N squared. So you can calculate the energy of an electron in a certain energy level by using this formula where N is the energy level. So this gives you energy of an electron in a certain energy level, but there's another formula that gives you energy of an electron's transition. So if electron is transitioning between initial Ni and final Nf, you can give that change in energy as Rydberg's constant, value is negative 2.178 times 10 power negative 18, 1 over Nf squared minus 1 over Ni squared, where I is the initial, or where the electron started the transition from, and F is the final, where it ended. Sometimes you are asked to calculate these changes in energy. Now, before I go further, I do want to emphasize here, remember all these early theories of atom came about by studying the nature of light. And sometimes kids still get confused and ask, what is the purpose of studying nature of light? Because see, the atom is so small that scientists cannot really look inside the atom. So they know the nature of light very well, and they study the interaction of matter, which is atom, with light, and then by studying the changes in light, they try and extrapolate the nature of atom. That's why there was a whole lot of study of light. And remember, light is electromagnetic radiation, and all electromagnetic radiation travel at the speed of light, c 3 times 10 power 8 meters per second, and c is equal to lambda nu, where lambda is wavelength of light, generally in meters or nanometers, and nu is frequency in 1 over second or hertz. There is another formula here, c is equal to E is equal to hc over lambda. Here you can calculate energy of a photon, which is a quantum of light, by using hc over lambda, where h is Planck's constant, 6.626 times 10 power negative 34 joules second. C is 3 times 10 power 8 meters per second. Lambda is wavelength of whichever color photon you're studying the energy for, or calculating the energy for, and it is generally in meters. If it is in nanometers, you'll need to convert it because C is in meters per second, so units cancel out. So these are the two equations you need to know in terms of photons, energy of quantum, and light. One thing I want to remind you here is this is energy of one photon. This is the formula for calculating energy of one photon or one quantum. So if you had to calculate energy for 1 mole of photons, how would you do it? You'll calculate energy for 1 photon just like that and multiply that by 6.022 times 10 power 23, because how many photons are present in 1 mole? That is Avogadro's number. Alright, moving on from there, let's get to atomic structure and the current model. The current model of atomic structure is called Erwin Schrodinger's wave mechanical model. And this model was put forth by, there were a lot of theories and discussions before this model was put forward, but the two very important ones that you must remember is de Broglie's hypothesis of dual wave particle nature and Heisenberg's uncertainty principle. Berg's uncertainty principle, saying that it's impossible to find exactly the speed and the location of a particle. And that gave rise to Schrodinger's wave mechanical model. And Schrodinger's wave mechanical model could explain the spectrum, emission spectrum of even more complicated atoms, and it stands true to today. So what is Schrodinger's wave mechanical model? It says that the atom looks like a beehive. Bees buzzing in and out of the hive. So you have a center nucleus and electrons are buzzing around it, and the area around the nucleus, I'll draw the nucleus in green, where the probability of finding electron greater than 90%, this is called electron cloud. So what makes up an electron cloud are various orbitals. Please distinguish orbitals from orbit. Orbitals was a term coined by Schrodinger. They are totally different from Bohr's orbits. Now, how did he come up about the nature of orbitals? So what did it look like? So Schrodinger considered atom as wave, and when he applied the property of atom, electron as wave, not atom, electron as wave, then he applied the property of electron as wave to the wave equation. He got three functions for it. Each function pointed to a characteristic of electron or orbital in which the electron is present. And these functions, after solving wave equation, were called as quantum numbers. And each pointed to a particular property of electron or the orbital in which the electron was present. We have three quantum numbers, n, l, and m. N is principal quantum number. It can have values of 1, 2, 3, 4. It does not have value of 0. Okay, the ground level is called 1. So this is the energy level in which the orbitals are present. L is, it defines the shape of orbital. So based on this, Schrodinger could say L's value is 0, meaning one value for s orbital, and he could say that s orbital is spherical. Then L's value of 1 means p orbital, and it is dumbbell shaped and can have x, y, or z orientation. 2 value of L means it's d, and 3 value of L means it's f. If theoretically you get any value more than 3, we don't have any more orbitals discovered beyond f at this point. So s, p, d, or f. And you can calculate L as 0 through n minus 1. All values between 0 and n minus 1 are possible L values. Then ML's values are negative L to positive L, and they talk about the orientation of orbital, the 3D orientation of orbital where electron is present. For example, S, if L is equal to 0, meaning s orbital, then ML can only be 0, because negative L to positive L means it has only one orientation. But for P, it could have negative 1, 0, positive 1 values. So that's how quantum numbers work and define the properties of orbitals. Now moving on from there, SPDF orbitals, we're going to see now how the electrons are filled in orbitals. And I will have to add another slide, but you can continue on the same big paper. So let it populate here, and then I'm going to go over so it is populating that one over here. Let me see if I can new slide, blank slide. Okay, so now I'm going to talk about filling of orbitals, or filling of electrons in orbitals. Okay, filling of electrons in orbitals is dictated by three rules of Bow's principle, Hund's rule, and Pauli's exclusion principle. Aufbau's principle says that electrons tend to occupy lowest energy orbitals. So remember, we write that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. So this dictated that 3d comes before 4p, right? So this was Aufbau's principle, and you must remember exceptions to Aufbau's principles are copper and chromium, where it is, instead of being S1D9, it is actually S0D10. Oh, I think I switched them around. And the other one between these two is S1D5, oh sorry, D4 to S0D5. The reason for this is half filled. D5 is half filled, and completely filled D is more stable than partly filled D. I might have switched them around. Please check your periodic table. Now Hund's rule says that no seconds rule. Remember, where pairing of electron in degenerate orbitals does not happen till every orbital has had one electron. This is applicable to filling in the p sublevel. So S will pair because it is the same orbital, but in p these three are degenerate of the same energy. So if you had to fill 2 electrons in p, you will not fill them like that, but you will give each one 1, and that's Hund's rule. And Pauli's exclusion principle says that no 2 electrons in an atom can have all 4 same quantum numbers, and that's why there was a spin quantum number added later with a value of +½ or -½ spin, one for counterclockwise, one for clockwise. So even if 3 other quantum numbers are same, the 4th quantum number would be different. And with filling of orbitals and quantum numbers, I would like to now move on to 2 more keywords which are related to filling of orbitals. They are called para and diamagnetic. Remember, para and diamagnetic. Paramagnetic are substances that can show magnetic properties. They have unpaired electrons, and the only way to figure out paramagnetism or diamagnetism is to draw orbital diagrams. And talking about drawing orbital diagrams, so filling of orbital lead to electron configurations. And how many types of electron configurations have we studied about? We've studied, one is called just expanded electron configuration. So let's take, for example, magnesium. Okay, its expanded electron configuration will be 1s2, 2s2, 2p6, 3s2. Then there is condensed. Condensed for magnesium will be, you write the noble gas neon, then 3s2. And then there is orbital diagram. And generally you write orbital diagram as condensed, so neon, and then you'll draw 3s as box and electrons as arrows, so 3s2. The other thing here with electron configuration is electron configuration for ions. Remember, the outermost electrons are lost first. So magnesium ions electron configuration will be, it becomes like neon. Can you tell me what will be Cr plus's electron configuration? It will be Ar. That's it. You don't have to write 3d10, you can if you want to. So AR 3D, I'm sorry, 5, not 10, 3d 5, and the 4s, so really it was AR 3d, why do I keep writing 10? Neon, oh gosh, what am I doing? That was, let me start over again. Okay, so chromium is AR 4s1 3d5. Cr plus will be Ar 3d5, not 4s1, because 4s1 gets lost. Remember, even though 3d is higher energy than 4s, 4s gets lost first because it's outermost electron. And with that, I'm trying to think if there's anything else you want to remember. I think one other reminder here is, remember Mercurus is Ag2 2+. Ideally Mercury has two states, Ag+ and Ag2+, but it's been found that Mercurus does not exist as Ag+ but Ag2 2+. And with that, Unit B's review podcast comes to conclusion. Have a good day. Thank you for listening.